Hello, my name is Ben Huang, and this is the Lab 1 presentation for constant velocity and Newton's second law. So, the introduction. The purpose of this lab was to analyze constant velocity motion and validate Newton's second law. We collect motion data of an object that is in constant motion using tracker, compare it with a computational model, that being the GLOW script. Preview, compare the differences between the predicted and the observed models, the predicted being the tracker and the predicted being the GLOW script and the observed being the tracker, and explain how different assumptions may have affected the accuracy of the models. Moving on, these are the formulas that we used. We used the velocity update formula, we used the position update formula, we used the average velocity formula, and we also used, of course, Newton's second law. Again, also we did use Newton's first law, but that's not really a formula here. And yeah. Okay, so the system in our case is the moving object, that is the cart in our video, and the surrounding would be the friction on the rail of the cart, and the air resistance, gravity, as well as normal force, as well as, not mentioned here, but the applied force by the hand that is moving our cart. Our initial velocity is negative 0.2902 in the x direction, and 0, 0 for y and z. Our x initial is 0, 0, 0. Next slide. We have our predicted, which is given by our GLOW script, and we also have our actual graph, which is given by tracker. And these are just basic position versus time graphs. And again, these are going in the negative direction because we moved our cart in the negative direction, that being left. And yeah. So this is the GLOW script code. We are updating the position and velocity using the first script over here, which is just the position and velocity update formulas. Ball velocity plus F net divided by ball mass times delta t, which really is just ball velocity is equal to ball velocity because the F net is 0, and 0 divided by the mass is just 0, times delta t is again just 0. And the position update is just ball position plus ball velocity times delta t. And yeah, and this are our initial conditions again, just reinstating that. Discussion. What if we analyze your video data on tracker and you made a choice of orientation of the axes, i.e. plus x and negative x were interchanged? I mean, for one, we did ours with the negative x direction, so if it was in the positive x, the graph would go upwards instead of downwards. V would also be positive instead of negative because your velocity goes in the same direction as your position, and our F net would still be 0. So really nothing would change. Everything would still be basically the same except for which way the graph is pointing. And so if it was positive, graph pointing up. If it was negative, graph pointing down. Is it possible for you to say how many pushes and pulls, i.e. how many forces are being added together to give zero net force in the case that you observed? Discuss briefly. So all these forces will give you 0 when combined together because it is at constant velocity. So that constant velocity just means no acceleration, which is also why there's no, F net, of course. We have friction that's on the rail, and we also have gravity that's pushing on by the earth itself, and we also have the normal force, which is the rail pushing onto the cart in response to gravity, and we also have the applied force being that of our hand, and we also have air resistance. So these all combine into a net force of 0, and that is everything in our lab.